Hello, my name is Marcin Konefał. I will be talking today about our new Meta SDV platform, which targets the needs of SDV developers. So let's start with the introduction. Cars have changed tremendously since their first successful commercialization. It is especially noticeable when we look at the interiors of the modern cars, where we could find a touchscreen infotainment system together with digital cluster and minimalistic physical buttons. In fact, the scope of the differences is wider between the first cars and the state-of-the-art cars. Nowadays, the tempo of changes accelerates, and the shift in the vehicle design is mostly driven by software. The first cars, which were purely physical devices, have been transformed to the machines essentially defined by software, what enable us to move them into the virtual space, the meta space. So let's explore how we can use this meta space to efficiently develop and test SDV software. As you may remember from the previous presentations, hardware and software decoupling is one of the major design principles in Pleo's Vehicle OS. On this, on this foundation, we built the new Meta SDV virtual development environment. In this environment, we can replicate cars' behavior, test functionality of the software, and analyze its performance without physical prototypes needed at every stage of this process. It includes hardware emulation, which enables test software in isolation with 3D visualization of the emulated vehicle, recording data of the real car, which we can use to analyze them in the form of metrics in the virtual space, simulation of external factors like weather conditions, which affects vehicle behavior. Having this invaluable insight obtained from the virtual space, we can use them in turn to enhance the functionality, the functioning of the real car, closing in this way the continuous improvement loop. Depending on how we want to use the Meta SDV, we can divide it into two different parts, emulator and tools. Both of them could greatly facilitate the development process. How it is achieved explains Meta SDV development flow. Particularly, we want to focus on what you can do by yourself without relying on a build system. Here is how it looks like. As the first step, you can look at the below of the slide. We, of course, implement a service, and we use Vehicle API to communication with the rest of the middleware. Next, naturally, the next step would be to build it and link it with Vehicle SDK libraries. Then we run it. There is no hardware with which we can communicate. Instead, we can use Meta SDV emulator, which fulfills that role. We also provide intuitive web-based interface where we can look at the emulator state in 3D model of vehicle and change it in aim to evaluate and debug your service. However, if you need to perform more in-depth debugging or analysis, you have Meta SDV tools at your disposal. Please keep in mind that this development flow is not restricted to the developer's environment itself, but it can be automated and incorporated into a continuous delivery pipeline as well. In this case, the integration tests are enabled by Meta SDV emulator, whereas Meta SDV tools can be used to ensure the behavior of the system for predefined scenarios do not change unexpectedly. All that happen almost on the fly, providing fast, reliable, and valuable feedback for developers. The next step is to look in detail what is MetaSDV, and emulation is an absolute cornerstone. We'll talk about this in the first place. Let's start by naming the benefits which come from emulating the hardware layer in the vehicle. And there are in plenty. To enumerate the most important of them. Firstly, please take a note that the testing on the hardware is expensive because hardware is generally expensive by itself. On the other hand, testing on the software is much more cost-effective in both terms, time and money, and it also scales very well. Secondly, it is important that the information about development process is fed back into the process. When the software is tested on the actual device, the feedback loop is much longer. Thirdly, it is hard to imagine how much effort would cost to cover all corner cases while testing a new version of software by hand. A lot of them would be hard to reproduce in the real world, while it is much easier and safer to do it in the virtual space. For example, verifying the emergency lights if they automatically turned on when a car takes part in an accident, in a collision. Finally, when we are working on the software without hardware involvement, we can assure their decoupling. So if it is desirable, how we can emulate hardware? Let's look at the graph which illustrates the flow of information between the software and the hardware in the real vehicle. On the left, you can see Pleos Vehicle OS. It is collection of the core modules which defines car behavior. Any vehicle application is built on the top of that. Between the Pleos Vehicle OS and the physical car, we have a vehicle hardware abstraction layer. And this is where MetaSDV operates. If we look on the next slide, we could see that in the virtual environment, the Pleos Vehicle OS stays the same, but we replace the vehicle hardware abstraction layer with the emulator, which fully mimics the behavior of the hardware. Additionally, we have a user-friendly web-based interface illustrating the exact state of emulated device, the emulated frontend. The emulation of physical vehicle is a substantial thing, but we can go further than that. To make the life of developers easier, we identify the needs arising from software development, categorize them, and provide the set of useful tools. The first tool, Recorder, collects data from all available vehicle API communication endpoints, and it is applicable for both physical and virtual car. The received data are deserialized and stored into the database. This recorded data we can use in many ways. For example, firstly, as you may know, troubleshooting of the system consisting many services could be really challenging, especially analyzing its consecutive states. The investigation of the recorded data may prove to be much easier and more efficient in tracking down the problems. And secondly, the recorded data could be used to create test scenarios or train AI models. And finally, the recorded data would serve well in analyzing the functioning of the system. Particularly for analyzing the functioning of the for analyzing latencies, we have a special distribution of the recorder latency analyzer application. It works in a similar way to the recorder. It collects data from all available vehicle API communication endpoints. However, to determine latencies, we are rather interested in metadata of messages, particularly messages timestamps. Having these timestamps, we can calculate latencies together with additional measurements, store them into the database, and visualize live in the form of dashboards. The Pleos Vehicle OS itself is implemented by many services communicating with each other. During tests, often, we want to check the system state to ensure that everything works smoothly. Also, if you want to verify how newly delivered software behaves under specific use cases, we often need to enforce particular state of the middleware. The console is useful on those occasions. Not only does it have capability to check the state of a given endpoint, but it is also able to change it by injecting new data. In the last section, we will show more precisely how it is used in practice. But first, let's revisit the same development flow, which was described earlier in the presentation, one more time, but from another perspective. Again, firstly, we implement a new service, and we build it. Then we run, debug, and evaluate it. In the top right corner, you can see the picture of the emulated web-based interface. If we want to analyze it further, we can use the MetaSDV tools. In the bottom right corner, we can see the picture of the latency analyzer window. But right now, it's a moment to see some concrete examples. The first demo illustrates how emulator's web-based interface can be used. The interface is on the right side. On the left side, we have a terminal. And this interface has three main parts. On the left, we have tabs corresponding to vehicle components. In the middle, a list of vehicle components specific values. And to the right, the 3D visualization of the emulated vehicle itself. On the left, we have a terminal with a test application which sends vehicle API messages in the predefined scenario to imitate one of the Pleos Vehicle OS services. As we can see, emulator changed its state, so it reacts to the messages. But there is more. We can use this interface to manipulate the state of the emulator. By clicking on the specific value, we can change it. Having this feature it increases the flexibility with which we can use the emulator. Specifically, it facilitates the testing. It simplifies the setup of emulator state for specific corner cases. The second demo illustrates an example how we can use the latency analyzer application. It visualizes data in the form of dashboards. On the top, we have plots informing us in which states door lock and the load beam lights are, while on the bottom, we have illustration of latency values between the requested status change and the moment when it is effectuated. On the right, there is an application which sends these requests. This tool is especially useful to verify if the latencies on the highly safety critical communication endpoints, which are measured on the actual car, do not exceed specified norms. It would be essential in ensuring safety of the validated solution. The previous demo operated on the data indicating the normal functioning of the system. Let me show you how useful this tool can be for detection of the abnormal activities in the system. Here is a demo which additionally simulates the unexpected burst of the network traffic, which hinders the normal functioning of the middleware. We could notice that the canvas on the bottom have changed their color to red. It is caused by the dramatic increase of the latency values, which went beyond the level triggering the alert. As you can see, such basic analysis can tell us if a malfunction occurred in the system, and what is even more important, when exactly does it happen. It is a good initialization point to start drilling down what is exactly the source of the problem. The last demo shows how to use the console. The main window is divided into 3 smaller windows ordered in the column, and the log window at the bottom. The left column contains the control window. We can use it to update a state in the middleware by sending an update, while the middle and the right column are used to visualize the actual state of the endpoints. This functionality is similar to the manipulation which was shown in the web-based interface, but in this case, the console uses Vehicle API to manipulate the middleware. That is all what we prepared for today. Thank you for your attention. And do you have any questions?
그럼 지금부터 Q&A를 진행하도록 하겠습니다. 첫 번째 질문입니다. 메타 SDV 툴에서는 다양한 차량 아키텍처나 API에 대해 어느 정도로 커스터마이징이 가능한지에 대해서 문의 주셨습니다.
Okay, right now there is not a lot of customization, but for this year we provide the whole new tool configurator, in which we could define the particular behavior of each component. So we could sense if it is the configurator tells us to do so. For example, particular error from the devices. I'm not sure if that responds your question. We are still working on it, but the customization will be quite considerable to include every corner cases.
네, 두 번째 질문입니다. 에뮬레이터는 실제 하드웨어의 동작을 얼마나 정확하게 재현하는지에 대해서 문의 주셨습니다.
Okay. Right now, we are on the stage on the SEAL emulation. We rather emulate the software, which is near the hardware. But also, in this year, we'll start to simulate HIL, the particular hardware components, by using probably specific simulating signals and other ways to precisely simulate hardware.
네, 마지막 질문입니다. 현실과 메타 SV의 갭이 충분히 작음을 어떻게 보장하는지에 대해서 궁금해하시는 분이 질문을 남겨주셨습니다.
If we could be sure that the gap is sufficiently small between Meta and SDV world, that is a good question, but very open, I believe. That we will aim to make this gap as small as possible. Probably there is a perfection that it almost seems to look exactly the same. Probably, I hope this project will end with digital twin, when it will be hard to see the difference in the behavior, but it is a process. So the more work it would be put to Meta SDV, more it will be accurate and more close to the actual device.
그 마지막이니만큼 마지막 질문 하나 더 받도록 하겠습니다. 타겟 차량이 바뀌면 할 역시 대규모 변경이 필요한데 개발 차량이 바뀔 때마다 어떤 방식으로 변경하는지 궁금하다고 남겨주셨습니다.
I'm not sure if I understood the question. It was about if vehicle change, we also need to change Meta SDV and keep them aligned with each other. And I agree, it is considerable work. And right now, the vehicle is still in the progress, and we trying to keep up with the real vehicle. But sure, it should be taken into consideration.
네, 다시 한번 발표를 진행해 주신 마르친 코네파우님께 힘찬 박수 부탁드리겠습니다.